Okay, so I'm going to do a parallel RLC. It's out of your parallel RLC module, but really it's just an RL circuit. We'll get into the C when we do power factor correction. That's when we add a capacitor in parallel to help cancel out the VARs from the inductor and bring us close to a power factor of 1 or 0 degrees. But for this one, we just have a resistor and a motor, so an inductor. So a resistor of 103 ohms is connected in parallel with a motor that has a resistance of 34 ohms and an inductive reactance of 69. So this is right out of your blackboard. So similar to series, I'm going to set this question up in that kind of a table style. So we have our resistor, and we have our motor, and then we have our total, because these are the things that are in the circuit that are going to add up to our values of current. So in series we had different volt drops across different aspects of the circuit. Now we're going to have different currents because we're in parallel. So again, voltage is common for parallel, current is common for series. So my resistor I'm just going to draw as a horizontal line because it's at 0 in phase. These currents are in phase with the voltage. So I'm going to take this value of 103 and put that right here. And we're going to add that to a motor. Again, it's going to have a resistance and an inductive reactance. So it has a reactive portion, so he's going to have his own triangle. And then we're going to get a total that also is a triangle because we're going to have an inductive reactance and resistance as part of our circuit. So to give us the information here for our motor, it says it's got 34 ohms resistance and 69 ohms of inductive reactance. And it's asking for the total current. So it wants to know total current. That would be the hypotenuse of the current triangle. It wants to know what that is right there. So we can use Ohm's law to move down from this impedance section down to current. I can take this value, okay, it said this in the question, I didn't write it down, but it said it's at 120 volt, 60 hertz. Okay, so that 120 volts is across the other portions of the circuit. I'm going to draw the circuit down here underneath just so we can see what the actual circuit looks like. So we have a resistor in parallel with a motor that has both components at 120 volts, 60 hertz. Okay, so I could draw it like this, have 103 ohms here. For this resistive part, I'm going to have 34 ohms, and here I'm going to have 69 ohms. Okay, so that's kind of what the circuit itself would look like. So they're hooked in parallel. So when we use the voltage, we can get down to these currents. If I take 120 volts divided by 103 ohms, I'll get the current here, which happens to be 1.165 amps. Now you're going to want to try and do that with here and here. The issue is if we look at this branch right here, this whole branch down here is seeing 120 volts. So each individual component is not seeing 120 volts because they're in series, so they're going to split that voltage. And we don't know what that value of voltage is, but if we can find the total Z of the motor, then we can use 120 volts to find the total current of the motor. Okay, so that's what we're going to do. Don't find these values here, okay, with 120 because you're going to get it wrong. The other thing we want to do is I drew this here, but I want to make a point here to cross that out and say, do not total your ohmic values over here. The only way we could find the total circuit Z is by taking the total voltage of 120, dividing by this, and we'll find the total circuit Z. Okay, but that's only if the question asks for it. This one doesn't. But do not total your ohmic values because we cannot just add them up. Okay, it's in parallel. In series we could, but we can't in parallel. So we use Pythagorean theorem to find the total impedance of this motor, and I get 76.922 ohms. So then I go 120 divided by 76.922 ohms, and that's going to give me this value here, which is 1.56 amps. Now, I can't start totaling currents over, even though there is some in-phase components, is I need to find another piece of information. So to find this side, or this side, I'm going to have to use the power factor. So the power factor for the motor exists in all of these triangles. So you can find it in any one of these. This is the only one we can find it in. So if I take my power factor in this triangle, I'm going to go 34 divided by 76.922, and I'll get a power factor of 0.442. in this triangle, which is also the same in this triangle, which is also the same in this triangle. Not this one, because these two, that's the total volt or total current and total power for the circuit. That's going to be at a different power factor, but the motor power factor is going to be the same through all of these. So then I can use trigonometry or reverse this formula, which is trigonometry. Okay, I can find this side is 0.69 amps, and then I can use Pythagorean theorem or again trigonometry to find this side. Now that I have all the sides of that triangle, I can total things up because I can add the in-phase components and bring the out-of-phase components together too, whether they're inductive or capacitive, and then solve for a new total. So I can take 1.165 plus 0.69 because they're both on the horizontal, okay, or they're in phase with each other, and I get 1.855 amps. Now I can also bring this 1.4 over because it's going to add with any other reactive component in the circuit, but there is no other, so we just bring that straight across. Then I use Pythagorean theorem to solve for the total current, and I get 2.324 amps. So that is the answer to the question. Big thing is I can only bring this horizontal value down to this triangle by using the total voltage, the 120 volts. Then I have to use the power factor to solve for these two sides. Okay, then I can just simply add things across. Again, as long as they're in phase with each other, I can just add them straight up. And then we always solve for a new one. And then we could find the new power factor for the circuit by taking this number divided by this number, and we would have the power factor of the circuit. Okay, so that's kind of it in a nutshell. If I wanted any power values here, I can still use the P is equal to I times E. So if I went this value times my voltage, I'd have my watts here. So times any of these. Now I can use any side of these. I can times this by voltage to get the VARs here. I can times this by voltage to get the watts, and this by voltage to get the VA, and the same on this triangle. It's just this impedance section here where we only want to bring down this hypotenuse to the current triangle, and then we can just use the power to move around. Okay, so hopefully that helps you get through the first couple questions in your parallel RLCs.